Hey everyone, so we looked at V and W and torque and force and all those attributes that we can read out of the simulation, but we can also use in the simulation. And this is what we want to look at now, how to create a destruction basically purely by setting attributes. So we will not actually calculate any collision, and also keep in mind for now we will not look into constraints. That comes in the next chapter. For now, we just want to look at how we can destroy something actually quite simply by just adding our own or setting our own attributes. And this will actually look better once we have constraints with it. So for now, we will help ourselves by just deactivating everything that is not exploding basically, and just activating the pieces that are supposed to move. But keep the technique we use here in mind. You can of course combine that with constraints later on, and this will potentially look much better even. But you will see even without constraints, you can create some really nice destruction effects, and that's what I want to talk about here. So we have this tower here, and every piece is one object. And what we can do to turn this into packed objects, of course, is assemble. As you can see, I already created my Tommy just to be aware that this scale is more or less okay. So it's not too big, not too small, very important as we know. So thanks Tommy as always. And now we use an assemble and turn it into a packed geometries. And then we have 3000 elements here roughly. And now we want to destroy that thing. So first of all, let's start simple and we just make this thing simulated by adding a bullet solver. And then let's for now create the ground already because we know this is needed. Okay, so here we are. And yep, it implodes. So everything seems to work. Every piece is considered a single piece. And we just have to make sure it doesn't implode on the first frame because that wouldn't make sense. So we know how to do this. We use our good old activation workflow. So I do it with a point wrangle. I set the integer active to 0. So let's make sure we call this active 0 and we create a group. And we can already define the area where we want some kind of explosion to happen, which usually is some kind of spherical area. And let's put this on a number that I already tested to work quite well. And we choose roughly this area. Of course, depends on what you want. Okay, cool. So, and this we call this group active. Make sure it's actually a point group. And then we create a point wrangle to activate only those points. Let's call this wrangle active 1 because we set the integer active to 1. And really careful, make sure that you only activate the ones in the group. And what we should get is a bit of a hole that falls apart by itself. Looks like this. Which is already pretty good. Cool. So we have just parts of it that just fall down. But what we want is we want to give it a little bit of a, outward movement because it's an explosion. So we already know how to do this. Let's set the velocity, and for now just set something simple. So behind my head you would be able to see that the direction is actually positive x. So let's say 500, depends on your setup of course, when the pieces in the beginning should move in this direction. Let's see what happens. And as you can see, it does exactly what it should be. So pretty straightforward, nothing new here. We already seen this technique many times before. Great. The only thing is that looks a bit weird, right? It doesn't really look like how it would actually happen because we want some kind of radial movement. And for this, we use a technique we actually already know from the fountain example. So I want to show it on a grid, and I would just scatter a couple of points on it. And remember, what we used to do there is the cool thing about points is that their position in space is also the direction to the center. So what we did before is we set the velocity to the position. And when we show the velocity, we can actually see that they point, in this case, actually outwards, because remember, this is the tail that is shown outwards from the center. And the logic here is actually that you basically did the following. You used the position and subtracted that center. Now, the thing with the center is, in this case, it's a vector, the center currently is the center of the world, which means 0, 0, 0. And this is why we could just left it out. So let me quickly do this again with normal, because it's a bit easier to see. So instead of the velocities, we use the normal, and there you go. Now you can see it pretty clearly. And this is the logic behind it that we kind of used without knowing. We subtracted the center of the radial direction from the current position. Now this is cool because, yeah, this is kind of built in, but it has a couple of problems. The first problem is that the length of the vector is dependent on the distance. And this is because it's basically a vector between the center and the point. And the further it is away, the longer this distance is. There's an easy way to fix that. We just normalize our vector. And you can do this with the command normalize. Very important, always remember to normalize. And if I press enter now, you should see that all the vectors have now the same length, which is much easier to work with and gives you know, a better way of working. And the next thing is, okay, this is cool that it's towards the center, but isn't there some way to move that center somewhere else, maybe up here? And this is really what's already built in here. We just have to change this vector here. And what we could do ideally is we have some kind of object that we can move around. So we could use, for example, a sphere, which is cool because this is by default a primitive and has only one point. So by moving the sphere around, we essentially just move one point around. Another node that we could use is a control node, which is basically like a null in Maya, which is this kind of a locator. Exactly, a locator as it's called in other programs. I go with the sphere because the gizmo is a bit easier to control, but both is possible. It doesn't really matter. So I take the sphere and I put it into the second input, because what we want now, we want to read out the position of this sphere. And we can do this, of course, with a point function, because we want to read out the only point the sphere is made of. So we read it out from the first input. The attribute we want is the position, and the point we want to read it from is the first and only one, means 0.0. And if I do this, you can now see that this actually allows us to control where the center basically is, that the vectors are pointing currently away from, actually. If you turn this around, depending what you want, you can also, instead of saying p minus center, you could say center minus p, which then would make the vector point towards your sphere, which might sometimes be what you want. I don't know what you would do with that. But in our case, we want an explosion. So the vector should move away from it. So we move it back to the order we had before, which is current position minus the center, and then it points away from it. Cool. So we can actually steal that. Let's call that V. And we just steal it and combine it with the setup we already have. So this V we don't need anymore, and we replace it with our setup we just used. And to visualize it a bit easier, because it's always hard to show any kind of attribute on the packed primitives, I use an add to kind of kill everything except the points. And you can see this is how it looks like. Currently the normals, because we still have set it to normal, are pointing away from this object. So let's make sure we move it to something that makes sense, maybe something like this. Let's see where our area was. Yeah, that doesn't look too bad. Don't put it in the middle, because we want, you know, the explosion to the epicenter of the explosion, so to say, to be roughly here. And now let's make sure we actually change this to velocity, otherwise it doesn't work. This was really just easier to visualize. And now we connect this. And if we run this, we should now actually see that this works. Let's have a look. Yeah, something happened for a second. The problem here is the velocity is simply not strong enough, because the velocity is right now the length of the vector, which is normalized, which is 1. So what you can do, you can just multiply the whole thing with basically the strength or the speed you want. So let's say I multiply the whole thing with 5, and now the whole thing should be 5 times faster. And there you go. Now we see a little bit. And that might not be enough for you. So let's make sure that we allow you to change this. So I usually put this on a parameter. Let's call this speed. And there it is. And let's try 10, for example. And then we should see something that's pretty good. Yeah, that doesn't look too bad. One thing to keep in mind is it goes a bit more in the length than in the height, and that is because basically the pieces collide up here. You have to play a little bit with the settings to get something that looks good for you. Maybe 10 was a bit too much, let's say 5. But as you can see, you can just set the start velocity, which is a technique we already know, and this way you can actually create some kind of explosion. Actually, now I want the 10 back. By the way, by moving back the epicenter to something like here, let's say, then there will be more of an outward movement. So I'll play around with this a little bit to find the right position. Now, what is a bit boring about this is that all the pieces kind of move in a straight direction. We can make this more interesting later on by also giving every single element a random speed. It's actually quite simple, so let's quickly do this. You can, of course, just multiply the whole thing with a randomizer, and we just base that on the current point number, and there you have it. Now every single piece will have a random speed, which is probably looking even more interesting. You could use a fit range to make sure that the lowest speed is not 0. This might be sometimes a bit of a problem, but you can see very easily you can create a randomization on top of this. But what we want to look at right now is not so much the speed and the direction, because we could say we're happy with this, but the problem that they all kind of stay still, they don't rotate. And this could be the next point wrangle we add to this, because we've learned that we can add an angular speed with W. So let's do this. And as we know, W is a vector, basically the axis that it rotates around. And in this case, all we really want is a random axis every single piece rotates around, which means we need a random direction, which means, of course, we need a curl noise. So we feed that with a position, and this will probably not look much different because currently the result will be between 0 and 1. So there is something, but to make it a bit more visible, we can, of course, multiply this with a multiplier as well. I don't want to call it speed, but you could call it, angular speed. I just call it multiplier. So let's multiply that with 5, and then it should be way more visible what we just did. Because now every piece should have some kind of rotation. You can see it especially later on. One thing before we move on I would actually do is let's increase the resolution of our curl noise by just multiplying the position with a number, for example 5, to make sure basically that every object gets a different direction, and they're not, so that not pieces that are close to each other get roughly the same direction. Otherwise it's a bit boring. And yeah, something like this. So let me quickly do some kind of play blast or something, and then we can see how this looks. And while I'm at it, let's also increase the velocity a little bit, and then we should have a relatively good result. And here we are. Now you can see we have the velocity that moves it outwards and rotation on top. And it's pretty quite simple. And this is what I really want to show you. You don't need much to create an effect like this. You don't need constraints. You don't need any kind of meta balls or complex stuff in the dot network. You just have to assign attributes like W and V, or potentially you could have also used force and torque. But you can see it's really quite simple, easy to set up, and you can later combine this with constraints as well. So yeah, I hope this was helpful. Thank you very much, and see you later. Cheers.